All right, our topic today is applications of Cartesian vectors. So last day we looked at the idea of a Cartesian vector in the first place and what it would do. And the idea was that if we used components to try and represent a vector, it was a really nice way of doing it because we could do addition of vectors and subtraction of vectors very easily. It also meant that we could basically refer to a vector just with a couple of numbers rather than worrying about describing a direction and a magnitude. So what we want to look at today is just a way that we can use them. Now, don't get me wrong, we're going to be using Cartesian vectors for the rest of our vector unit, really. But this is our first sort of application of them. What we're going to do actually is we're going to look at some of the questions that we did from last chapter and see how we can apply them instead. So this here is meant simply as a reminder. What we were able to do at the very end of chapter 6 was we could take a particular vector and break it down into its horizontal and vertical components. So we had our angle theta there, we had our vector x, and basically what we're saying is that vector x is equal to the sum of a horizontal component and a vertical component. So just a way of breaking it up. Now, the way that we made that calculation was on the side there. Horizontal component was magnitude of x times cos of the angle, and the vertical component was times sine of the angle. The important part to remember was that theta had to be in standard position. And remember that meant that we were starting on the positive x-axis and rotating in a counterclockwise direction. Okay, so that has to be the way we refer to that angle. Once we do that, we can actually go straight to here. This is now a vector v in Cartesian form, in component form. So in the last chapter, we simply called them a horizontal component and a vertical component. Well, now that we actually have something to refer to with Cartesian vectors, we can just put it right into that form. So vector v, I'm calling it vector v now, is vector v times cos of theta and vector v sine of theta. That'll give us the x component and the y component. But keeping in mind, we need that angle in standard position. Okay, we're going to do two questions. Here's a simple one, and then the next one's quite a bit bigger. It says write vector v in Cartesian form if the magnitude of v is 30. So first thing I want you to notice, there's vector v, and the angle given was in standard position. So we're good to go here. We don't have to worry about making too many adjustments to this at all. We can just go ahead and calculate it. Vector v, we said it's magnitude of vector v times cos of the angle, and then magnitude times sine of the angle. So we knew that our magnitude was 30. Angle in standard position is 220. And we really should have a good sense of if this is going to work or not. Vector v is ending up in the third quadrant. So we better get two answers that are negative here. And remember, that was the advantage of picking an angle that was in standard position, because our cast rule kicks in. Right? The cast rule is going to force our trig ratios to be positive or negative. And in the third quadrant, the only thing that should be positive is tan. Both sine and cos should end up negative. I got 20.98, sorry, negative 20.98 and negative 19.28, which sounds about right. We've gone a little bit further left than we've gone down, which makes sense too, because that's a 40-degree angle. 45 would have been a perfect diagonal, right? So 40 has gone a little bit further left than down. So there's the idea. We've just calculated that. Now, one thing we looked at last day was how to get the magnitude of a Cartesian vector. And we did that using Pythagorean theorem, right? We'd square those two components, add them up, and then take the square root. You could do that now. Remember, the magnitude is supposed to be 30. And if you want to play around with it real quick, it'll only take you a second to calculate it. My guess is, though, you won't get exactly 30. And the reason for that is as soon as we did cos of 220 and sine of 220, we've rounded a little bit. So if you do get the magnitude and you tried that, you're probably going to get either just below 30 or just over 30. So keep that in mind. It's going to be off a tiny bit because we've done that rounding. Okay, this is our last question. So not too much to look at today, but this is really what we're building towards. Here's our application question. And you didn't need today's lesson to do this, right? This is a question that we've done before. It was questions like this on the problem set and in lots of homework questions. It's just a ship moving. Sailboats in Lake Huron. It's being pushed by the wind along a bearing of 80 degrees, so something like that. It's 80 degrees, 25 kilometers an hour, and I'll call it vector W for the wind. And then our current is at 320. Remember, we're doing bearing, right? So starting at north and going clockwise all the way around. So 320 degrees is, well, there-ish. And what was it, 4 kilometers an hour? And that was the current. I'll call that vector C. So we've seen pictures like that before, right? We could pick those, I don't know, I'd probably pick up the blue vector and move it so that they were aligned head to tail, and then we'd use a little sine law or cosine law and figure everything out. That would work, and it'll work fine. I want to show you this new way. What we're going to do is we're going to take both of those vectors and convert them into Cartesian form, and then try and do the calculations from there. And it'll work well. What I want you to notice, I want you to think back to the amount of work that would have been required in the last unit, and think about how much work would be required to do it this way, and just see if they're comparable, see if one way appears faster than the other, just for the sake of getting an idea of which one's better. I want to get vector W in Cartesian form. So that should be the magnitude of vector W, which is, there's 25, I think, right? Yep, 25 times cos of the angle. Now that's the angle in standard position, right? So standard position would be right there. That's just 10 degrees. So 25 cos 10 and 25 sine 10 will give us vector W. And it should be much further to the right than it was up. Sure enough, there's vector W. That looks okay. And then vector C, same formula, right? Magnitude of the vector, 4 times cos of the angle in standard position. So I'm not sure how well I can fit this in here. Sorry about that. Maybe right there. We need to go that far. So we've gone 90 plus a little bit more. We need to figure out this little angle here. But if the blue angle was 320, this has got to be 40. So the standard position for our current vector should be 130. 4 sine 130. And I've got minus 2.57 and 3.06. Much smaller numbers because it was a smaller vector, right? The magnitude was only 4 compared to 25 on the last one. Okay, so what we've done then is we've converted the red vector and the blue vector into Cartesian form. The advantage now is that if I want to get the resultant, all I have to do is add those two vectors up. And adding vectors geometrically is hard, right? Geometrically we added them last time, and that was when we have to use all our trigonometry. Cartesian vectors, it's really easy to add the vectors up. All you do is put the numbers together. So for this one, we're going to go the 24.62 plus negative 2.57, 22.05, and then 4.34 plus 3.06 is 7.4. And we get our result really quick. So that part happens very nicely. Let's see if I can get some extra space for us here. There we go. So we've got a result, and the only thing I would say is it's not really in a great form based on the way we were asked the question, right? We were told the question with kilometers per hour and a bearing. So giving an answer in Cartesian form isn't really good form. So we should be able to give an answer back in the same form that we received it. So I'd like to know the magnitude of this vector, but that's was relatively easy to do, right? We just use our Pythagorean theorem again. So if I calculate that magnitude, I get about 23.26. And I mean, these aren't perfect numbers, right? We've rounded already, so I'm not worried about keeping any exact values here. So I've got the magnitude. I need the direction too. And there's different ways you can think of the direction. But here's what I would recommend, and this has always worked well for Earth classes in the past. Just draw a little sketch of it. So here's my grid, and I want to actually sketch what vector r would look like. Vector r is at 22.05 and 7.4, so that's something like that. It's gone over 22.05, and it has gone, let me just put another color there, it's gone up 7.4. Okay, not to scale, it didn't matter. Once you see that, I just need to get an angle in that picture, right, to be able to describe the direction. So let's say I wanted to get that little angle there. And that's not the only choice, but it'll work. To get that angle, I'll do tan theta is 7.4. And we'll do a tan inverse of that, which gets actually kind of an ugly angle, 18.55. So there's angle theta. Not really the angle we'd want, I suppose, because we want to give a bearing. So I probably want that one. But now that I've got theta, I can get angle beta at the top just by subtracting from 90. Is it 70, 71.45 degrees. And now I've got an answer. I've got a magnitude 23.26 kilometers an hour on a bearing of 71.45 degrees. Okay. And there's our answer, that's done. So again, thinking back, our options were doing it this method with Cartesian vectors or doing it all geometrically in the last one. I like both. I mean, they're both really good methods. I don't mind the trigonometry. Sometimes it can be tricky to see all the angles. I know that was an issue that came up a few times with the homework questions in the last unit. But I think if you consider how much work we did and how much time it took, they're actually pretty close. I don't think this method here was much quicker than the other method by any means. What becomes interesting is if we'd added in a third vector. So let's say on this one, we had the wind, we had the current. Let's give this sailboat a little motor. So now it's got a motor as well. So let me even draw it in. I don't know which way that it goes. There's a motor pushing this way at whatever kilometers an hour. Now there's three vectors. Well, think about how we would have done that geometrically. To do it geometrically, you have to align those vectors head to tail. Well, you can't do that with three vectors and do a nice calculation because you end up with a quadrilateral instead of a triangle. So you'd have to do two vectors at a time, find the resultant, then add the third vector and do the same thing again. So adding in that third vector is a significant problem in the last chapter. Is it a tougher one this time though? I don't think so, because all you'd have to do is find the new Cartesian coordinates for that vector. That would have just given us, what, a vector m for motor? Would have given us one more set of components to find the result, and we just would have added them up. So, I mean, the amount of work, it would have added one more of those steps to get an extra vector, and then you'd add them again to get vector r. So adding in a third vector here doesn't do too much. The steps at the end would be exactly the same no matter what. So a huge advantage for our Cartesian stuff. It doesn't matter how many vectors we use, it isn't going to add a significant amount of extra work. Whereas geometrically, adding in extra vectors can be a real mess. Imagine trying to do geometrically with 7 vectors, right? Which is a problem not that we're going to deal with, but from a mathematical standpoint, it's fairly realistic. With Cartesian vectors, it makes no difference, right? Relatively easy calculations here. Okay, that's it for today. Hope that went okay.